Alright, welcome to part 2 of 3.2 interactions between molecules. Now we will be looking at the bottom three boxes there. So dispersion forces, which exist between all molecules. Their strength depends on the size and shape of the molecules. And dipole-dipole interactions. They exist between polar molecules and their strength depends on the polarity and the size of the molecules. Predict the relative strength of interaction between molecules given relevant information. And finally, you will have hydrogen bonding. It is a particularly strong form of dipole-dipole interaction that exists between molecules. You need to be able to draw diagrams showing partial charges and hydrogen bonding between HF, H2O, and NH3 molecules. You also need to be able to explain the boiling points of hydrogen fluoride or fluoric acid, water, and ammonia in terms of hydrogen bonding between the molecules. Now I'm going to jump to slide 9. Okay. Now let's talk about dispersion forces. Now, all molecules have dispersion forces. However, non-polar substances only have this force, dispersion force. We'll watch the video of how do geckos defy gravity later on, or you can click and watch it too. Let's talk about strength of dispersion forces, what affects it, and how does it become larger. Larger or heavier molecules, so if the molecules have got a lot of mass, higher molar mass, they would have more electrons. More electron means temporary dipole that occurs would have a lot more negativity. So yeah, a lot more electrons, that means creates larger temporary dipole. That means stronger force of attraction, well, i.e. the dispersion force would be occurring to the particular molecules or substance. This leads to also explanation of higher melting point or boiling point. Alright, moving to comparison between methane and octane. Now methane is known usually as a gas. CH4 is a formula. Octane is H18. It's a main component of petrol. Methane at room temperature is gas, whereas octane is liquid. It's part of petrol. TM, melting point, is negative 182 degrees Celsius and octane is negative 57 degrees Celsius. For boiling point, methane evaporates at negative 161.5 degrees Celsius. So it's gas since a while ago. But for octane, it only evaporates at 35 degrees Celsius. So hotter day, octane will be evaporating. I should go back. So hopefully you can see the effect of the size, so the molar mass, and also number of electrons available, and both are non-polar. So yeah, dispersion force is the only secondary interaction that's available for these, aren't they? So hopefully you can see here that the higher the molar mass of the substances, the higher the interaction and also boiling or melting points. Alright, so that's for dispersion forces. Let's now move on to dipole-dipole forces. In the polar molecule, such as HCl that you can see in the diagram there, they are permanent dipoles. Permanent. It's no longer a momentary one like dispersion force. Like H and Cl, because chlorine has got higher electronegativity, there would be always a negatively charged end, and also positively charged end, dipole-dipole. So if you have got more than one dipole molecules, they would be interacting. That's why we call that as dipole-dipole forces. Larger differences in the electronegativity of atoms involved in each molecule defines how strong those polarities are. So larger permanent dipoles would be obtained, and stronger dipole-dipole forces between molecules occur. Which means if a bond has got higher difference in electronegativity, well, I've got oxygen, hydrogen there. Oxygen, hydrogen is fairly different if you compare the electronegativity. But if you compare that to hydrogen and fluorine, fluorine is further away. It's on the right hand side of the periodic table. So there's higher difference between hydrogen and fluorine compared to electronegativity difference between these two, hydrogen and oxygen. So this would have higher force of interaction. You can compare that by also drawing PCl3 and a PF3. Have a go at drawing those two molecules of each and how they would be interacting. Alright, moving on to the extreme case, much stronger case of dipole-dipole. We call that hydrogen bonding. Why? Because hydrogen need to be part of that. How polarity makes water behave strangely is the video that I attached, and we'll watch that together. Opposite charges on the permanent dipoles of molecule create electrostatic force of attraction between molecules. Now that's straight off, copied sentence from dipole-dipole, so you don't have to even write that. It's just a repetition of it. Hydrogen bonding, though, is an extreme case of dipole-dipole. What does it mean by that? Hydrogen bonding is only available if you see oxygen to hydrogen direct bond, nitrogen to hydrogen direct bond, or fluorine to hydrogen direct bond. If you don't have those direct bond as part of something, like for example, if you have nitrogen and hydrogen, so nitrogen and hydrogen, there are two more bonds that's available. That could be linking to something else. Unless you have this component, or OH, oxygen and hydrogen, and linking to something else, or simplified version would be water. That's something you're familiar with. The hydrogen bonding would not occur. Okay, so for hydrogen bonding, you need to look for OH, NH, or FH. O, N, and F, those three are found in periodic table far right at the top, meaning they have got higher electronegativity, and they create very strong permanent dipoles when bonded to hydrogen. Hence, you call that hydrogen bonding. Let's try drawing a diagram for hydrogen bonding between H2O and H2O. So try drawing this and use dotted line between those two molecules. Ammonia, NH3, and another NH3. So this nitrogen would be interacting with this hydrogen here. Draw dotted line. Same thing for HF and HF. You can do it this way, but as long as you can draw dotted line between molecules, that's something you just need to be able to draw. There's an example for water already there. Okay, summary of those forces there. So for dispersion forces, I'll zoom in. Dispersion forces, this applies to only type of intermolecular forces for nonpolar molecules. Relatively speaking, if you compare dispersion force to other types of interactions, it's fairly low. But if the size of molecules increase, stress depends on, I'm just reading that, it can overcome or becomes even stronger than hydrogen bonding. It just depends on the size of molecules. Relative boiling point is also low if you're looking at similar size molecules. Dipole-dipole forces. It's available for polar molecules. Dispersion forces still present on polar molecules as well. So on top of dispersion force, dipole-dipole will be applied. Okay? Relative strength would be medium because we have got hydrogen bonding, which is stronger. Strength depends on the differences in electronegativity of the bond of the atoms in the bond, and also the number of polar bonds available. And the boiling point is also around the medium range. If you look at hydrogen bonding, it's an extreme case of dipole-dipole. So, and dispersion forces are available for everything. So dispersion force is present on top of that if that molecule contained HO, HN or HF direct bonds. Yeah, it can cause hydrogen bonding. Strength depends on number of polar bonds compared to non-polar parts of the molecule, and boiling point would appear as very high. Alright, so secondary interaction itself, a bit more information, and I think this is the last slide too. The strength of secondary interaction between non-polar molecules. Well, if you are looking at non-polar molecules, you'll be looking at dispersion force. What does it depend on? That's something you need to be able to explain. Finally, the strength of secondary interaction between polar molecules with similar molar mass. So you'll be looking at dipole-dipole. Explain how boiling and a melting point would change in terms of their intermolecular forces. Alright, that's it. That's the end of 3.2. I'll see you in the next video.